All right, here we go. So, way too easy. Well, fitting lines of data points, I mean, it's kind of an obvious situation at times. And what I mean by that is the data that we've got there. If we take a look at, say, this table, and what would you ballpark that data is going up if you had to go and say it's following this type of a graph? What is it sort of kind of maybe as you look at it? Is it curvy? Is it kind of straight? Would be your first thing. So does this look sort of kind of like it in a line? So when I look at this, it might appear that it would really work to go and model this as a linear model, linear fashion. Okay? And that's kind of what we want to do is take a look at this and say, hey, what is it going to look like? What is it kind of go? What is it going to give us? So the idea here that the first differences of data output are constant for uniform inputs, okay, basically means that it is going to fit exactly. Nearly constant means it's kind of close. So if I go back to what we've got here, and I take a look at the information that's going up, sorry, back up, there you go, nice. And I take a look at the data that's here. I've got this, 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 this. What is it roughly going up by? Approximately. Well, let's see. Here to here, it's about 5,000, right? Well, here there's a jump of close to 10, but here it's about 6,000. Here it's about 3,000. Here it's about, well, at 13,000, that's a jump and a half again. So, I mean, there are some big jumps in there, and then there are some that are smaller jumps, right? But put together with both males and females, they kind of fall in a line, right? Now, kind of close, kind of the same difference. I mean, if I look over here at the high school graduation, where was that? Where we had that big jump? Over, I'm right here. Some high school, here to here, versus here to here. It was a fairly good sized jump. Okay. So we got this idea that's kind of linear. It's not going to be exact, is it? I mean, the points don't fall on a line going straight up. So, let's take a look at retirement. Now, we got the annual retirement payment to a 60-year-old retiree with 21 years or more at the Clarion State University as a function of the number of years for the first difference of the outputs. Okay, now, he's getting 40,000, 42.9. Does it go up at a constant rate? Always going up by the same amount? 1950? That's what it's really looking at. So, you guys heard of this thing called slope? Slope is simply a constant difference between first, second, third, fourth, fifth. Remember how when you would kind of look on this on a graph when you first looked at it, you'd rise over run? It's like steps. It's always up the same amount and going forward the same amount, up the same amount and going forward the same amount. That's what's going on here. Now, as you go and take a look at this in the form of a linear equation, when I get down here, what's the slope? 1950. That's exactly the difference between each one of these. Okay? So there's a lot of things that are interconnected with this that you already know. You've already done. You've already played with these things. Okay? Now it's just applying them to say, hey, this is what we can use this for. So, let's see. Let's look at this one here. Okay? So, plotted out the payments, drew the line. Easy enough. But I got a question for you now. Does that mean if I wanted to get the year 21.5, does that mean that it's gone up so much? Is he getting paid that amount? Halfway between the numbers? Does that mean in July that he's getting halfway between 40,950 and 42,900? Is he getting halfway between that? Okay, put it to you this way. If you got your job and you start your job first of the year, you have to wait 1 year before you get your raise. And your raise is that $1 an hour pay. And you get a $1 an hour pay raise every year that you work with this company. Does that mean in July you got a 50-cent raise? So this kind of gets us down to this idea of the difference between a discrete function and a continuous function. Now, we can model this with this idea of a continuous function. But the continuous function is only useful, only gives us good information on the years. Because for that whole year, 21, he's getting paid the $40,950. For that whole year 22, he's getting $42,900. It isn't slowly rising. It jumps, okay? Like I said, it steps. So you got to kind of be able to keep an eye on that and understand the difference of what's going on. Okay. So here we go. Health service employment. Is this discrete? I cannot say discrete. Is this going to be an exact or an approximation? Wrong one. This is discrete data. In other words, does it go up by the same amount all the time? Well, if I look at 513 to 592, it looks like it's going up approximately, or it's going up exactly what? 79? Is that the difference? And if I add 79 onto that, do I get to 688? And if I would add 79 onto 688, does that get me to 705? Obviously not. So we can draw out the plot of this. And they got the plot sitting right here. So as I look at that, it's going, okay. Doesn't really give me good information, does it? Well, actually it does give me all kinds of good information. It tells me that the data is approximately linear. Now, they give us an equation here. The graph of the equation, y is equal to 16x plus 510. They put that in there. Is that good? Is it close? Is there a better one? Probably. Now, they gave us this equation. They didn't tell us how in the world they came up with this equation, did they? If we go back and read the data that we were given, it doesn't necessarily just gives us the equation and determine whether the line appears to be a good fit. So, I look at this and we say, it's not really a good fit, is it? Is there anything about it that seems appropriate, though? Would its slope seem appropriate? If we take a look at the dots going up and we take a look at the line, do we get a feeling that they're kind of going up at the same rate? So the slope would probably be a good thing. Now, there are a couple of ways of dealing with this stuff. One of the ways is to pick a pair of points that appears to be in a nice little line. So I'm going to grab this here for a second and show you what I mean. So as I look at, whoops, sorry. How many points do I need for a line? Hello? How many points do we need for 2? So if I wanted to, I could go through and draw a line starting at right here, and I could extend that out through that. I'm just going to, okay. Does that work? Say I wanted to go through the center of that one there. Is that a good line? Let's see. What would happen if I did this? Let's see. Could, let's see, I'm going to make this one. Let's see, properties. Let's make it red. Let's do this. I want it to go through those two lines because I'm saying to myself, you know, what's in the middle would be a better thing than what's on the ends. Is that a perfectly legal line? Will it represent the data appropriately? Will it give us a ballpark idea of what's going on? And the answer is yes, in all those cases. So one of the things that we can make sure that we do is utilize the exact same procedure every single time. Now, one of the things that's going to happen when we're working on this stuff is that we are going to be having to come up with a line of best fit. The best way that I can tell you to do that is to use a graphing calculator. The graphing calculator will take into account all of the data. Everything that is there, it will take into account for when it goes and calculates it out. So, with no further ado, grab your graphing calculators. Alright, so, always so temperamental. Now, whenever you do this procedure, always reset the calculator. You know, second plus 712. Now, cleared out all the data so you don't have to worry about that. First thing we're going to do is we are going to put in the data. Now, that information is always going to be up there, okay? Shows you how to go and do the plots on it. So, press the stat key, edit, press enter. All of our domain data information goes into L1. Everything that is range goes into L2. So we are going to put in 0, 5, 10, 15. Oops, no, we weren't counting by that, were we? 11, sorry. That carried away. 12, 13, 14, and 15. Okay? So make sure that you've got that data in. Now, arrow key over to the next column and put in that information. So we got our 513, always make sure that you check to see if you've got the same amount of data in both. Okay. So far so good? Yes? No? Got it all in there? Okay. Next step. What we want to usually do with this is try and give us a plot so that we can see our data. Okay. So what I want you to do now is go to second, y equals, and you'll see this screen. Press enter. We want to be on plots 1. Now you see it flashing on the just press enter. We want it to make sure that it's going to be there. Okay? Now, it gives you the rest of the stuff that we need. X list is going to come from L1, Y list comes from L2. Tells us that the type is going to be dots and the marks are going to be little squares. And of course I get the added event color. Okay? So, now, window. When you're going through and doing this, you have to make sure that you set your window for appropriate viewing. Now when I look at this, I see it goes from 0 to 15, so 0 to 20. Give myself a little extra room. Now, why minimum? What is the smallest value that I have in my domain? Well, 513, so I'm going to put in 500. Maximum value goes up to 771. Well, I'll go up to 900. Give myself a little room to play with. Okay? And I hit graph. So, do I have a model of the data? Did it come out and show me what I wanted to see? Great. Now, next step. I want the equation of a line out of this thing. So we're going to press the stat key again. And what we are going to do is go over to number 4, which is a calc. Once we are at calc, we are going to go down to 4, linear regression. What this is going to do is it's going to go through and do a linear regression on the data. So AX plus B, A is going to represent slope, B is going to represent y-intercept, and we've got the equation of a line. So it's on that, I press enter, and then it's like saying, hey, do you really want to go through and do this? And yep, arrow key down to where it says calculate, press enter. And I now have the equation of a line. Now the nice thing about this is the equation of this line is exactly what I need to go through and graph all this information. So what I'm going to do here is make sure that I have the equation of my line written down. Always write it down. So y is going to be equal to, let's see, 17.73. X. I mean, I got that repeating number in there. Do I need to deal with that any worse than that? No. Plus 509.917. Will that work for me? Okay. Now, go back to your calculator, hit y equals, and we're going to put that equation in. Yes, ma'am. You got different numbers than what mine came out to be? Then what you have to do is you got to go back into stat, edit, and look at these values. Did you get all the right numbers in there? Okay. Everybody's numbers close to mine? Okay. So that means something got put in there wrong. You missed a number, and that's generally what that means, because otherwise Everybody's calculator is going to be the same. And this is part of the reason why I want you to use the calculator or some level of technology in order to do this. Because you're always going to get a consistent equation. Okay? Okay. See, if you go and pick points like what I did here, you will have things that are right, but they're going to be a little different than somebody else's. And just for the sake of consistency, we'll use that then. So we're going to go back to the y equals, I want to put in 17.73x plus 509.917 graph. Now, I have got a line that is going through the data. I can use this equation now to estimate, figure out what other possible answers could be. I've got a model now that I can use for whatever I need to do. Yeah, I did use that word model. Okay. So, as we look at this, they came up with the equation and they've got a few different ones here. Okay. They used different points. And the thing is, you can use the same idea to go and take different points, go and calculate out what things are going to be. But I like using the technology and the calculator to run through and do that all the time, so I don't have to worry about things being inconsistent. Okay? That's where we get to this here, where it's called fitting lines of data with linear regression. Okay? It takes a little bit. That's why we like this idea that the calculators can go through and do this a lot faster. And it can go through, you can do this manually, but again, you've got the technology. What's the point of going through and doing it manually when we're looking for the understanding of what's coming out of it? Okay. So, these are the steps that you need to go through. Enter the data into a list, create a scatter plot, graph the utility, graph the function, report the function and or numerical results that make sense. So, that's why going through doing this is going to give you a good equation every single time, and everybody will have a certain level of consistency. Okay? Okay. It says, after a model for a data set has been found, it can be rounded for reporting purposes. However, do not use the rounded model in calculations. Do not round answers during the calculation process unless instructed to do so. When the model is used to find numerical answers, it should be rounded to what agrees with the context of the problem, usually 2 to 3 decimal points. Now, we had kind of a weird looking number. It had all those 3s after it. Put as much information in there as you possibly can. Okay? So, I do believe yeah, now you can also do this with a spreadsheet, and I don't like doing that. Okay. What I want you to do is I want you to, this information here, I want you to go and put that into the calculator. Now, let's see, how do I want to do that? Now, a lot of times when we're doing this, you've noticed this, that it talks about years after something. Okay? Years after something. So, do you really want to have your years to be all of that? 1,960. Generally, we pick a point and we calculate thereafter. An easy one to go and use is usually 1900. So you're only really worrying about the last digits. Sometimes you could take this from, 1960. If you wanted to go and do that, you could do that as well. So, what I want you to do is I want you to put the data in here, from here into your graphing calculator. And I shall do the same thing too. question is then, which one is the data that's represented here? Well, the first is obviously the input, right? The second, it says output population in millions, right? Now the last one is first differences in output, differences in population. Now the differences, when we talked about that, that was to help us determine, is a line a good fit? Well, in this case, the numbers are fairly close, except for probably that last one, so linear is a good thing. But what I want to put that in as my information, I don't even have any data for 1960 for that one. So our input and our output is what goes in. So it'll be the 180, just what's over here. Okay. So let's see. Pull it up there. Okay. Now, everybody got those numbers? Like I said, get the stat, edit, make sure that all the numbers are in this. So I got 0, 5, 10, 15, 20, 25, 30, 35, 40. Okay. Oops. That one there doesn't know. It's got the 303 in it, so it's got all the data into it. Oh, I see where I got messed up. 227.726. That would make a bit of a difference, wouldn't it? So I hit enter. Now my data looks better, so I go stat, calc 4, enter. That look better? Okay. Now, one of the things that we also have with this is something called the correlation coefficient. It tells us how good of a fit it is. So what I want you to do, I want you to press the second key, and I want you to press 0. It says catalog down there. So you should be in the catalog screen now. Once in the catalog screen, what you need to do is scroll down to the D section and find something that is called Diagnostics On. Now, whenever you reset the calculator, it automatically goes and shuts the diagnostics off. So what I want you to do is arrow key up to where it says arrow key to where it says diagnostics on. Press enter. Enter again. So now the diagnostics are on. what I want you to do now is go back to Stat, Calc, number 4, and now you'll see that we've got some more information here. We have r squared and r. Now r is what is called the correlation coefficient here. Whenever we're taking a look at the correlation coefficient, it is always going to be between -1 and 1. Okay? The closer to either end, the better the fit is. The negative just identifies whether it's got a positive slope or a negative slope. So my correlation coefficient here is 0.997. 0.997 isn't too bad. It's pretty darn close to 1. And we've got a positive slope, so that matches up with it. So that tells us that we've got a pretty good, strong relationship here. This is a good model. Now, if the value is closer to 0, once you hit 0, there's no correlation. It's just like a shotgun pattern on a piece of paper. Okay? It's all over. There is no pattern with it whatsoever. Okay? So, please keep that in mind, and I'm going to let you guys get